Okay, so that was one direction. Now let's move the opposite direction. So let's assume item 1 and item 2 are true. And we want to construct the semigroup. And we construct the semigroup by the negative exponential sequence. So where's my box? So this will be my definition of the semigroup. And then I want to look at it in the limit as n goes to infinity. And here is another typo. I'm sorry about that. This is to the n. To the n. That's very important. So this limit is then supposed to go to the semigroup T of t. To do this, so we first rewrite Tn as by factoring out t to the n, t divided by n to the power of n, and we get this guy here. And then the resolvent arises for nt instead of lambda. Now the resolvent is bounded for n divided by t bigger than omega, than the growth bound. So this means this is okay for large n and for small t. And these are the two things I'm interested in. In the end, I want to send n to infinity, naturally. But I also worry about t to 0, because at 0, I need to get the identity. Next, we want to show that Tn at 0 is the identity. And here we can do what I actually mistakenly did earlier. So we can just take this to the power of minus 1. So we get I minus Tna to the minus 1. Because if Tn at 0 is the identity, then the whole thing to the minus 1 instead of minus n is also the identity. So, and then we take u in the domain of definition, and we write it in a funny way by using the inverse of t minus, the inverse of 1 minus t over na, and the operator itself, so nothing happened, but then we can multiply it out, we get a first term and a second term. And then we look at the difference of this term, so basically Tn with the minus 1 instead of the minus n, u minus u, and we use the identity from before, so we get a t over n in the front, we get this inverse here, and we get a u, and the inverse is a resolvent, so we have an estimate for this, we call this like c, so what we get is ct times the norm of au. Norm of au is bounded because u is in the domain of definition. And so then if this goes to 0 for t to 0, showing that the Tn at 0 is indeed the identity. Next I want to show that this converges to the semigroup. And for this I differentiate once more. I do d by dt of this Tn. So I get an n to the front. So here I have the right exponent. Now it's minus n minus 1. I get an inner derivative minus a divided by n. So together this is then this term here. And now I argue for a function in dA squared. So it turns out I will need to apply a twice. So I use a domain of definition for a squared. And since dA is dense in x, dA squared is dense in dA. Something we can think about. So this means dA squared is also dense in x. And so then we can do this following beautiful and long calculation. So let's go through this. Of course, I want to show it's a Cauchy sequence. So I look at Tn of t applied to u minus Tm of t applied to u. And I can write this in a funny form as an integral over the derivative. So think of this backwards. If you integrate this, then you have Tm t minus s, Tn of s given at t, which is Tn of t, minus the whole thing evaluated at 0, which is Tm of t. So this is correct. Then you do product rule, so you apply the derivative, so we have little dots here, here and here from the product rule. And then you apply the previous result 8.11 for the derivatives of the semigroups. So you get the a's and you get I minus t over n a to the power of minus n minus 1. So here this is for m, and here is a semigroup you keep, and here is the semigroup you keep, and here is the derivative for n. Okay, So in all this, you can identify common factors, which is the m term to the power of m minus 1 and the n term to the power of minus n minus 1. And these are collected then here. These are common factors. And then we just balance whatever we keep. From the first term, we have a minus a, and we have the n term. From the last term, we have a I minus t minus s over ma and the a term. And then all this, not forget the u at the end. Okay, so now the first bit I keep, and I know these are bounded by what we have done before. And the thing in the square bracket, now the many things cancel. So there's an a here, which cancels with the identity term a there. And then there's an s over n, t minus s over m, and an a square applied to u. So then we get this term here. Taking out the bounds, the two bounded bits, then we can integrate. This is just an easy integral on s. So let's just do that. And we integrate all this bit. And so this is basically 1 over n plus 1 over m times r square u. And now as n or m go to infinity, this whole thing goes to 0. And we get Cauchy. Yoo-hoo! So then we can say t of t is in fact the limit n goes to infinity, Tn of t. Now, there's one little thing which we still need to show, and that is to ensure that the semigroup is our semigroup we were looking for. So does it satisfy the differential equation? So for the semigroup property, we differentiate Tn of t minus s, Tn of s ds. And we can write this in the following form, using the definition of the t's. Using the relation 8.12 for n is equal to m. So where is this? Here's 8.12. So I use this relation without the integral. And I said n is equal to m. Okay, so there's lots of stuff going on, but here it is. And then I can show as n goes to infinity, all this goes to 0. And this means t of t minus s, t of t derivative is 0. So t of t minus s, t of s is independent of s. And so it must equal a number we know. And this is the number if s is 0, which is t of t. So then this means we can take the limit, and we do this in 8.11, which is right here. So then we can take the limit there, and we get this guy also converges to t of t. And we get our differential equation right down here. Okay, so that's a proof of the Hille-Yosida theorem. It is indeed rather involved, so I hope breaking it down into 4 steps might actually help to get this all sorted out.